tonight's, let's look at tonight's homework for a second here. Tonight's homework, I need you to understand, has nothing to do with what we're doing in class today. It is our first, I guess second, application problem involving differential equations. It is going to push you, not break you. But tonight, definitely, this is going to be at least a 30-minute question, even for the best and brightest of us if you're doing this.
So this is today's classwork?
No, homework. You guys know Thursday I am not going to be here. Unfortunately, that is beyond my control. My job is changing a little bit, and I am protecting my teaching time as much as I possibly can. But right now, this part's out of my control. So Thursday I will not be here. Thursday is going to be a work day for you guys, from like start to finish. Okay. All right. So questions on homework tonight?
Oh, wait, this one?
Yeah, that one
Never mind.
is the homework tonight, which is a nice application problem involving differential equations. Okay. So, big brains. Here we go. Logistic growth curves. This is the direction that we're going. Oh, here you go, sir. All right, Lucia, can you start reading the where we've been?
Where we have been.
Bye.
By this point, as calculus students, you should be very comfortable with the following ideas. Given a differential equation, use integration techniques for separation of variables to generate a general solution. If you are also provided with an initial condition, generate a particular solution. Starting with a word problem involving the trigger phrases directly proportional and inversely proportional, set up a differential equation, then generate the particular or general solution. Given a slope field and initial condition, sketch the particular solution to the corresponding differential equation.
Okay. Is everybody familiar with all the things that Lucia just read? Okay. We're okay. Good. So that's what you know so far. This application problem right now is just an extension of what you know so far. I would expect that all 7 of you, of course there's only 5 of you right now, should be able to do this whole problem from start to finish completely on your own. If you're able to do that, great, go for it, work through this problem. Can you say focus, please? Okay. Problem number 1, you should be able to go all the way through completely on your own. I want to give you a minute or 2 to get started, and then we'll talk.
Is this your birthday, Miss?
Huh?
Is this your birthday?
Stay focused. Yes, but I was told that. I already asked. Yes. But this is fun.
Is this guy putting it?
Inactive.
We'll talk. Homework done. Homework. All right, town of DeRocheburg was founded in 1972. Yes, that's when I was born. When 1,000 people moved to the mountains of Colorado. No, that's not where I was born. Rate of growth of the population is directly proportional to the population at any time t. 2012, DeRocheburg now has 50,000 happy residents. A, using this information, determine an equation which can be used to determine the population of DeRocheburg. Where do we start? Where are we starting here?
The equation, the dp over dt. Please.
Okay, so you set up the equation dp over dt equals k times
T. Oh,
k times t or k times p?
Oh, I put t.
You put k times t. Go back and read the problem. The rate of growth of the population is directly proportional, that's a key phrase, to the population at any time t. dp dt is telling you how the population is changing, right?
Oh.
It is changing in such a way that it is directly proportional to the population. So there should be a dp dt equals k times p. Thank you. All right. So with that, now what do we do? We got a couple of choices to make here.
Isolate the variables.
Okay, you're going to isolate the variables, separate the variables, which is a very specific calculus technique. That is a way that we can do that. We can multiply both sides by dt, we can divide by p, dp over p equals k dt. We have separated the variables, congratulations, first point earned. Now what? Okay, integral on the left, integral on the right, usually one of them easier than the other. You've heard me say these things before. The integral of dp over p.
Natural log of p.
Natural log, careful, not of p, but natural log of the absolute value of p. And the integral of k dt is k times t plus c. If you successfully integrated the left and successfully integrated the right and have the constant of integration, you're up to, just leave it on my desk, you're up to 4 points already. Now what?
The p by itself.
You want to get the p by itself? Okay, that is a move, that is a valid move. Another thing that you could do.
Use one of the, I guess, information that you have in the top and plug it in.
Right, there is information that was given to you guys in the beginning that we would call the initial conditions. What are the initial conditions there?
0,
That's a 2,000.
Okay, so depending on how you look at this, you've got year and you've got population, and I think I told you guys, what, 1972 and 2012?
Yes.
In 1972, we've got 1,000 people. In 2012, we've got 50,000. But I didn't hear anybody say, let's actually use 1972, because that would just be some ugly number crunching that we need to do. Let's call that times 0. So 1972 times 0, 2012 times 40. Great. Now, most of you guys, I think, have become really big fans of solving for the dependent variable and using the initial condition later. For the sake of opening your eyes a little bit more, let's actually go with it. Let's go with this in this form. So if t is equal to 0 and p is equal to 1,000, then that means the natural log of the absolute value of 1,000 equals k times 0 plus c. So natural log of 1,000 is equal to c. Great. So now I've got natural log of the absolute value of p equals kt plus the natural log of 1,000. Okay. Plug in the other one. If t is equal to 40, I know that p is equal to 50,000, so the natural log of 50,000 equals k times 40 plus natural log of 1,000. Okay? And my goal here, solve for k. Okay, let's see how clever we can get at this. If the natural log of 50,000 equals k times 40 plus the natural log of 1,000, and I want to solve for k, I'm going to subtract the natural log of 1,000 over to the other side, freeze. Natural log of 50,000 minus the natural log of 1,000. Right? If I've got a natural log minus a natural log over here, that is the same thing as saying natural log of their quotient, 50,000 divided by 1,000. So I'm going to get natural log 50 equals k times 40, so k is 1 over 40 times the natural log of 50. Great. Still not done. Doing some beautiful mathematics. I'm working up a sweat, but we're not done.
If you use a function.
Right, I actually need to figure out what p is as a function of t. So if I go back, I've got that the natural log of the absolute value of p equals 1 over 40 times the natural log of 50t plus the natural log of 1,000. My goal is to solve for p. Need some really clever mathematics here. Anybody have any? You want to exponentiate, right? That's how we get rid of the ln. Now, here's where I want to be careful. Exponentiate, exponentiate. The e to the natural log of the absolute value of p, the e and the ln are inverses. They cancel each other out. Over here, though, you might be tempted to say, oh, the e and the ln cancel out, the e and the ln cancel out. The reason that these guys canceled out is the e and the ln are inverses in the right way. That's not the case over here, so I can rewrite this and say, how about e to the 1 over 40 natural log of 50 times t times e to the natural log of 1,000. Legal? Brian, why is that legal?
Because when you multiply them together, it just equals just equals that.
Right, the bases are the same, and if I'm multiplying them, the rule is add the exponents. So it's legal. E to the ln of 1,000 is going to be 1,000. So the absolute value of p is 1,000 e to the 1 over 40 natural log of 50 t. Last thing to do.
I'll take out the two there.
Right, we're going to say that p is either plus or minus 1,000, 1 over 40 natural log of 50 times t, but we're really smart, we're really clever, we know exactly which one to go with. The positive or the negative? The positive. How did you make that decision?
With the initial condition.
It always goes back to the initial condition. If your initial condition is positive, you're going to have to pick the positive. You could also make the argument that, wait a second, if p is population, is the population ever going to be negative? No. So it's going to have to be something like this. Yes, sir?
We use PERT if we avoid.
Yeah.
Like, would they count that if we use PERT instead?
Yeah.
Could you use PERT? Could you jump straight over to PERT?
Yes. we
Why?
keep that.
Victoria, why?
Because I always remember the trick to go to PERT is d of certain variable over
Yep.
whatever it's d over the other variable that they use equals k times the first variable.
Right, it's always like d of your first variable dt equals k times your first variable. This guy here is the exponential form. What I want you guys to be able to do is just sort of see this and go, wait, I know what's going to happen. I know the end of the story. I know it's the exponential growth model. And look at where that went. What's that 1,000?
The beginning.
That's my initial population of 1,000. This p is going to tell me my population at any particular time. I have to do a little bit of work over here, but oh my god, we could definitely have done this without all this beautiful calculus going on behind the scenes. We're okay?
Is that a yes?
Is that a yes? What's the question?
Can we instead of doing auto equals go all the way to PERT?
If you see this right away, can you jump all the way over to PERT at the end? Yes. This will never happen on the free response because all the really big brains see the connection and they're like, I know it's PERT, why would I have to prove it? You don't have to prove it, you get to use it.
So we'll get the point.
You wouldn't get any of the points.
Really?
Well, you would, but they're not going to ask you this question.
Oh.
This should be a quick thing. They're going to ask this on multiple choice and you want to jump right over to PERT. Now, if I asked you guys to find doubling time is just how long does it take for the population to double? One of the things you guys would have done back in Calc or pre-Calc, you'd say like, oh, my initial population is 1,000. What am I really asking?
When does it turn to 2,000? I mean.
How long does it take for the population to become 2,000? That's not a calculus question. That's like an algebra 2 pre-calculus kind of question.
Mm-hmm.
Here's what I'm really curious about is your answer to part C. According to your model, what is the value of the limit as t approaches infinity of p of t and then I want you to explain the meaning of your answer. This will be our last A-B conversation for the week. So go get me, what's that limit as t approaches infinity, and what does it mean?
Say your prayers.
What's the limit of
What's the limit as t approaches infinity of your population?
So that's T.
Don't overthink this.
I know, what's the limit of T?
Trust the instincts.
Zero. Infinity.
What does it look
Set the
It's
population
an exponential model, right?
Yeah.
So as t approaches infinity, what happens to the exponent? The exponent's going to approach infinity.
Can you approach infinity population? Like infinity times
Okay.
population?
So you're having all the right thoughts. The calculus question, though, is what is the limit? What is it? What's that limit as t approaches infinity of p of t?
Infinity.
It's infinity. Now, the calculus works. As t approaches infinity, I'll tell you, I don't know what natural log of 50 is, but I know it's a positive number. Okay, positive number times 1 over 40 times something approaches infinity. The exponent approaches infinity. E to the power of infinity is infinity times 1,000. Even more infinity. So what we're saying here is the population approaches infinity. How do we feel about this?
Not really.
Why not?
You're just saying that I'm pretty sure you can get a population that's infinity. Just like
I love it. You're pretty sure, but maybe there's some room to be wrong here.
Sure.
Could the population of DeRozierberg in the mountains of Colorado be infinity?
If it
I'm
stays like that
well,
equation, yeah.
For a specific area, if the maximum of people in that certain population had to reach at some point, saying that
So I draw a circle, I say, here's the town lines of DeRozierberg.
Yeah.
Could I have infinitely many people?
You stack as many people up.
No.
Okay, so we're going to start stacking people, we're going to start compressing people, are you going to have an infinite number of people? You know the answer to this is
No.
no. An exponential model doesn't work. It doesn't actually describe what's going on because you have this limit. You're going off to infinity. That makes no sense. No sense. Okay?
until we do.
Until you do. But in Algebra 2 and pre-calculus, this is all that fits in your brain. Welcome. Welcome to Calculus BC.
So are we done with all AB?
No. For this week, it's Calculus BC. Alright, so I want to introduce you guys to the logistic growth model. And Roger, if you wouldn't mind, I need you driving the laptop. Okay? So, I want to introduce you to the logistic model. And where are my apes, people? Is no one in AP Environmental Science?
Me.
Have you guys talked about the S-shaped curve?
A-shaped curve.
S.
I think we all
Oh, yeah,
talked about the
before-
A-shaped curve.
Yeah, we
Or
did.
the S-shaped curve or the J-shaped curve?
There's two
Isn't
of
it the
them.
one that looks like,
And it goes like, it's kind of like
How do you zoom this thing?
It's not.
You know how to zoom this?
Okay.
There's one exponential, and then there's one
You know how to zoom this?
looks like an S shape, but it starts like stabilizing.
Stabilize?
Yeah,
Okay, Roger, you okay back there?
Yeah, I'm just in the-
Alright, so,
so that was a yes.
alright, good, you've seen this. Alright, Chepe, can you read the introduction here?
A more realistic model for growth assumes that the growth is bounded by the environment factors such as
Food.
food, or economic factors such as limited resources.
Okay, so I'm the mayor of DeRozierberg. I know I cut you off there for a second. I cannot support an infinite number of people in my kingdom.
You can.
I just went from mayor to king. I know, stay with me.
You're special.
Okay. Why can't I support an infinite number of people?
You're gonna run out of food.
I'm going to run out of food. What else?
Limited resources.
I'm going to run out of space. Basically, I have a resources, right? Also, like, people are going to start being like, I'm kind of crowded here, right? There's like sort of like group think here. Like, it's not advantageous for us to continue growing. Some of us maybe have to leave DeRozierberg. And I vote for Chepe as well. Okay. Logistic growth assumes that you know what's called the carrying capacity, the limiting capacity. And we're going to keep going. Chepe, keep reading.
In this the model, the rate of increase or decrease of the population at time t is jointly proportional to quantities y and L minus y.
So now we have another kind of proportionality. We have direct proportion. One goes up, the other one goes up, and they're related through multiplication. Inverse proportion, one goes up, one goes down, they're related by division. Jointly proportional means that I have one quantity that is directly related to the product of two other ones. In this case, y, if I want to think about this in terms of like population, and L, if this is my limiting capacity or my limiting population, then L minus y would be like available population. So if I'm the mayor of, let's go for it, emperor of the Rogerberg, right? I've got a population, but I also have like a maximum population I can sustain. We figured out that the maximum sustainable population is 10,000. What I'm saying is that my growth of the population is directly proportional to the product of current population and how much is still left. So if de Rogerberg can support 10,000 and my current population is 2,000, the amount left that I can support
8,000.
is going to be 8,000. It's how much I could support minus how much I currently have. And just like you know the exponential model, and when you see it, you're like, oh, jump to PERT, this guy here is your logistic model. And because this is Calculus BC, and because I want you to fully understand the beauty of the math, we are actually going to go through and solve that differential equation. I will blow your minds and lose all 7 of you at some point. And it is okay. I'm going to go way too fast, but it's okay.
So it's okay to drop down to AB?
No. What I want you to see, though, is the form. I want you to see this and recognize logistic growth. Just like you recognize exponential growth, the things you're looking for, rate of change in my population, directly proportional to 2 things. What are the 2 things?
Current population.
My current population and,
Yeah.
careful, not the limiting population. The limiting population is a part. The y is current population. L is the limiting population, but L minus y.
Oh, zero graded.
It's like the available population that I could still support. It's a product, it's directly proportional to the product of the 2. So here's where I want to pull out the graphing calculators, which is why you're all the way back down. So a certain national park is known to support at most 100 grizzly bears. 10 bears are known to be currently in the park. Assume that the bear population is logistic in nature. That is, we assume the rate of growth is directly proportional to both the population and the limiting factor at any time measured in years, with proportionality constant k equal to 0.001. All I want in this first one is set up the differential equation. We're just going to write it. So what is it?
Make the variable.
So we've got dy over dt, and then what?
Equals 0.001.
Okay, we've got the k, the 0.001. dy dt is equal to this guy, and then it's directly proportional to the product of 2 things. Your current population, which we're going to call y, and the available population. How much more could I support?
100 minus y.
100 minus y?
L minus y.
L minus y? Go back and read the problem again.
10 bears are currently in the park.
10 bears are currently in the park. What is that? What's the fancy word for that? It's the initial condition. I have, right now, I know that at time 0, my population is 100 bears. What I haven't heard from too many of you guys is what goes in here.
Yeah.
What's this part? K is your proportionality constant. Y is your current population. This guy over here is your available population.
10 out of 100.
Isn't it 10, not 100? Oh, because there's 10 bears. Thank you. What goes in here?
You shouldn't just be
100 minus 10.
100 minus 1.
I want to be careful. It's not going to be 100 minus 10 because my population is changing, right? Y represents the population at all the times. This guy is going to be 100 minus Y. So the y is like population at any time. At any time. The 100, that's your limiting population, or some people call it the carrying population. Right, that's the most I can actually support. The 100 minus y is what I like to think of as my available population. All we're doing right now is like take the information that they gave you and write the differential equation. Is everybody okay with writing the differential equation? So here's what I want you to do, and this is why Roger's back there. I want to use the calculator to generate the slope field. What I don't want you to do is draw the little lines. You could do that, but I'll switch over here. It's locked, and I cannot give you my password.
Aw, you can trust us. Why you do?
There we go.
I bet it's last digits.
So I want to get that going. So, right, you go to graph, it's option 7, differential equation, and you want to type in that over here. But be really careful. So 0.001 now times y, except with the differential equation it's not y. If you look over here, this tells you everything. Your dependent variable is what they're calling y1. So Roger, over here where you've got x, get rid of the x. Delete the x and type in y1. And I think you're going to need a multiplication sign between the 0.001 and the y1, and between the y1 and the parentheses. 100 minus y1.
Didn't work. Oh, never mind. You messed up.
Oh, what's that? 100 minus y1. Make sure you've got that typed in. What's that?
That's how it looks like.
Maybe.
Mine says invalid.
Maybe. What?
24,
Wait, what are we doing?
what's this?
Okay, right now we're just graphing the slope field.
Oh.
And depending on your window, you might have a lot of different things happening here. I want to pick a smart window. This is your time. This guy here is your population. So let's pick a smart window here.
Can we just eliminate the negative because you don't?
Right, if time is on my x-axis and population is on my y-axis, it doesn't make any sense for me to have like negative values for x, and it also doesn't make sense to have any negative values for y. So we're going to adjust the window, just hit OK. Now, if I menu, window zoom. Okay, everybody getting something like this?
Yeah.
Okay, help her out. Okay, now,
What is it?
if y represents your population, what has to go here? What would be a good window for your population?
Cool, it says what I said first time.
Y 100.
Click on the multiplication.
Most 100.
At most, my little island can support 100 grizzly bears. So let's change the window. So menu, window zoom, window settings. We're going to change the Y max. Did you guys hear the part about Y 100?
Yeah.
Okay. Y 100. Okay, go. Wait, did you do that?
That was magic.
Why 100?
Okay. I want to change the X a little bit. Change the X to like X max of 100.
Why?
Wait, yours has like more lines than mine.
Just change the field resolution to 20.
Yeah, so it's about the resolution that you have. Don't worry too much about the resolution. If it has more lines or less lines, that's okay. So what this is, this just represents your slope field. The idea of a slope field, though, is that it helps you just determine what the curve looks like, what the solution looks like. And I think we have an initial condition.
At like y, I mean at x equals 0, there's only like 10 grizzly bears.
Right, at time 0, I have 10 grizzly bears. So if I said, okay, time 0, here's 10 grizzly bears. This is just my guess, right? This is 0, 10. what I want to be able to do is use my calculator to give me a good estimate of what the solution curve looks like. And the way that we do that, go back to hit tab,
You get 0.9043.
okay, and go up so I can see y1 prime.
Oh, there you go.
Right. Your initial condition, this is the x naught, y1 naught, so put in 0, and then 10, and then hit enter. And that is your solution curve. And if you pay attention to the slopes are telling you exactly how the curve has to bend. It starts to flatten out up here at the top because I have a carrying population of 100. I'm not going to have more than 100 bears. Big picture, is everybody okay?
Is it an accurate curve or?
Is it an accurate curve?
Yeah.
What do you mean?
Is it an accurate curve of the like differential equation? Or?
Yes.
All right.
What's up, Jimmy?
Wait, what's the domain for that?
What's the domain for that? I think the domain we used was 0 to 100.
Yeah.
Oh,
Okay. Is everybody generally okay with the shape of the curve?
yes.
No? You're not okay with the shape of the curve? 0 to 100, and then 0 to 100 for the y min and the y max. What you might want to do is check your differential equation.
So why did we choose x?
Why did yours come out like that? That's a
Why did we put
good
100
question.
for the x? Why did we put 100 for the x max? I'll just guess. All right.
100 minus y.
Oh, no, never mind. He came back.
Okay, it was just going a little bit slow. All right, we're going to come back around to that in a little bit. Big picture, are we okay?
Yes.
Why is this a better model? Why is logistic growth going to give you a better model? Lucia, why is it going to be a better
Because
model?
when the limit as t equals infinity, there's like a set number where you have that maximum amount of grizzly bears.
Right. Unlike exponential growth, where you'd be like, "Phew, just keep going on forever. Grizzly bears make more grizzly bears, make more grizzly bears." What's going to happen is my curve, it starts to flatten out. Where does it flatten out? It flattens out getting closer to a carrying capacity of 100 grizzly bears. Big picture, we're okay? Now, there are some calculus questions that I can ask you at this point, and then there are some that I just cannot ask you at this point, that we are just not fully prepared for that. Okay? So, we're going to roll with the punches right now. So we've set up the differential equation. We sketched it with the calculator. If I asked you to evaluate the limit as t approaches infinity, you guys would all tell me. The limit as t approaches infinity is
100.
100. Okay, and what does that 100 mean? It's the parent, but if you were going to explain it to like a 5th grader, what would you say?
Maximum capacity.
Yeah, how much it can hold or whatever.
Right, I can hold no more than 100 grizzly bears. Now, if I dropped into the space, and this is the beautiful part of this, and I didn't plan it. If I dropped into the space 200 grizzly bears, just think about this. Forget about the math. What should happen? I dropped 200 grizzly bears into this space.
Including with the 100?
If my initial condition is 200, I drop into this space 200 grizzly bears. What has to happen?
Shouldn't it decrease?
It's going to have to decrease down. What I want to do is let's change the window. Change the window so that we can consider what happens with 200 grizzly bears getting dropped in. So we're going to change the window, not the x min and the x max, but the y min and the y max. So it goes 0 to like 200. Hit OK. Now, why is the red curve still showing up? Wait, what?
He's still using 1.
The red curve represents the initial condition. The red curve doesn't represent dropping in 200 bears. The red curve represents 10 bears. Try 200. So if you go back and you adjust, if you hit tab, and arrow up, change your initial condition instead of 0 to 10, or put in another initial condition, that's fine. 0 to 200. And now hit enter. what's happening?
Decreasing.
You're decreasing towards this carrying capacity, right? The land can't support 200 grizzly bears, and so what's going to happen, their malnutrition's going to happen, right? They're going to die. It's very sad to think about, but that's what would happen if you go above your carrying capacity. They have to die. They're going to approach that limiting capacity.
But it wouldn't go less than 100 then?
But it won't go less than 100 because basically what's going to happen, your population is going to stabilize at 100 bears.
Oh, okay.
Okay? Check.
So, with this problem, instead of 100 basic bears per unit, and we had 200, do we need to equate it?
But it would still be the same differential equation to begin with, right? Which gives you the same slope field. What would be different if we said 200 bears, you've changed your initial condition so that you're not starting down here, you're starting up here. But the limit as t approaches infinity would be the same. Okay? All right, we're gonna go as far as we can with this. Roger, you've done a great job. You can join us. Page 3 is not accidental. Page 3 is optimistic.
Whoa. Hey, listen, do you remember this?
We are optimistically going to solve this problem. This has nothing to do with tonight's homework. This is just a little morality lesson for Anthony. Don't miss class ever again. All right. So dy dt is equal to k, not k, 0.001 y times 100 minus y. And what I want to do is I want to solve this differential equation. And I'm going to go fast. Faster than usual.
That's
Bomb.
Can you upload this video to it as well?
I'm going to. Hence the camera. Big time. Okay. We get a differential equation. We want to solve it. What are we going to do? Separate the variables. So what that means is dy equals 0.01 times y times 100 minus y dt. I want to separate the variables, but I want to do it the right way.
we need to distribute.
I could distribute, and I will tell you that's going to be the wrong thing for us to do. What I'm going to do is I'm going to move all the y's onto the dy side. Why? Because it works. So what that means is I have dy over y times 100 minus y equals 0.001 dt. Have I separated the variables?
Yeah.
Yes. So now I integrate both sides. One of these, very comfortable.
The left one.
Yeah, the left one. The right side is going to be 0.001 t plus Charlie.
Yeah.
The left side is beyond your current abilities.
Maybe just distribute the y.
And I am not saying this to be mean, I'm saying this to be honest. It is beyond your current abilities.
Can you give this one?
What we're going to do is we're going to rewrite this part's not beyond your abilities. Okay, I'm going to rewrite the left-hand side this way.
What do one of the y and one of the
And I actually am going to break this into two different fractions. It's called partial fraction decomposition. You don't know this yet, but the big idea is this. I'm going to take this guy here and rewrite it as something over y plus something over 100 minus y dy. It's going backwards in algebra. Normally you have two different fractions, two different denominators, and you get a common denominator to get to one simple fraction. We're going to go in the reverse. And right now, just have faith. The numerators are 1 over 100 over here and 1 over 100 over here. You don't need to know where they're coming from right now.
No.
There will come a time. Just have faith. I worked this problem out like 3 times this morning. Okay. Equals 0.001 t plus Charlie. Now, the advantage of having two separate fractions, I can integrate this fraction separately from this one because I can distribute the integral. Okay? So, if I've got 1 over 100 in the numerator, well that's a constant, so I really have 1 over 100 times the integral of 1 over y dy plus over here, 1 over 100, times 1 over 100 minus y dy equals 0.001 t plus c. There's a little bit of hand waving over here, but it's hopefully okay. Integral 1 over y dy, you guys know?
Natural log of
This has to be, not natural log of y though, natural log of the absolute value of y. The integral of 1 over 100 minus y. I'm going to count on your smarticle particles here.
Absolute value of 100 minus.
Take the substitution.
Okay, you could do substitution, and we would identify 100 minus y as the baby. We would find the derivative of the baby, and the derivative would be a negative 1 dy. What winds up happening is that your integral is going to be minus 1 over 100, the natural log of 100 minus y, equals 0.001 t plus Charlie.
Can you just multiply all that by 100?
Okay. Yes, but hold on. Is everybody kind of okay?
Yeah.
Yes.
Okay. You are not going to have to do this ever. Except for Anthony. Okay? I really like this part over here is when a miracle happens.
Yeah.
Okay? But everything else, what's the next move?
Exponential.
Big picture, where are we trying to go with this?
Okay, y by itself.
You want to get y by itself, right? Solve for y. Get a y over here, get a y over here. This is going to be ugly. It's going to be ugly. But I know I've got some fraction killers in the room. So I'm going to multiply by 100. And if I do that, now I've got the natural log of the absolute value of y minus the natural log of the absolute value of 1 minus y. 100 times 0.001.
Isn't it 100 minus 1? Not 1.
Yep, that too. 100 minus y. 100 times 0.001 is 0.1 t plus, I'm just going to write c. Brian, why is that legal?
With the Charlie?
Yeah, why didn't I write 100c?
Because it's just also Charlie.
It's right. It's that super Charlie idea, right?
Oh, yeah.
I have a constant that I don't know yet. If I multiply by 100, it's still a constant that I don't know, so it's okay. All right, good. My goal: solve for y. Get y by itself. We got a problem.
2 y.
I got a y over here, and I've got a y over here. Shh. I need more people to know log properties than just him. Natural log minus natural log.
So y
Oh,
over
division.
100 minus.
This is the same thing as the natural log of y over 100 minus y equals 0.12 t plus c. I want to solve it for y. So we exponentiate both sides. E and the ln are inverses. Absolute value of y over 100 minus y equals e to the 0.1 t times e to the c. I think we've done this enough that you guys should be comfortable with that part.
Yes.
Okay. And e to the c
C.
is really just my friend Super Charlie here. So the absolute value of y over 100 minus y equals c e to the 0.1 t. And I know you guys are comfortable with this part too. Get rid of those absolute value bars. So y over 100 minus y is plus or minus c e to the 0.1 t. But this plus or minus c, why bother? This is c e to the 0.1 t. Sweet. Y divided by 100 minus y equals c e to the 0.1 t. God, I love it! Love it! What are we trying to do?
Solve for
Yeah,
y.
y by itself.
You want to solve for y. And I got a y in the numerator and I got a y in the denominator.
Can we just give up?
No, never! I got a y up here and I got a y down here.
Is that the same thing
We
as
did it.
y over 100?
And they don't cancel, no.
Multiply 100 minus y.
We can separate them. The variable.
I'm going to multiply both sides by 100 minus y. Spoken like a fraction killer. Or cross multiply if you want to say it that way. So on the left you have y. On the right, c e to the 0.1 t times 100 minus y. But now I've got a y on the left and a y on the right. Almost as bad as a y in the numerator and a y in the denominator. We're not going to divide by 100 minus y because then we're all the way back over here. But the legal thing that I can do now, I can say, oh, this means that y is 100 c, oh my gosh, 100 c e to the 0.1 t minus c e to the 0.1 t times y. And what's the goal again? I think I've forgotten. My old man brain, I forgot what we're trying to do here. I want to solve for y. I've got a y over here, and I've got a y over here. And so my goal?
Oh, wait.
What do you want to do?
Can you just add the last part to both sides?
Is that legal?
Yes.
And why is that better?
And then after that, you can factor out the y, and then you get y squared.
Okay. Oh, I was with you until you said that.
What?
That's
Okay, because every day we're going to add the c e to the 0.12 ty over to the left.
Never mind.
And on the right, you've got 100 c e to the 0.1 t. And what I heard you say was factor out the y. Is that legal?
Yes.
Yeah.
Yes. And that's better because look at what you have now. You've got 1 plus c e to the 0.1 t equals 100 c e to the 0.1 t. That's so good!
So it's 100 t e to the power of 0.1 t.
Y equals 100 c e to the 0.1 t over 1 plus c e to the 0.1 t. I have solved for y. But what's c? Could we figure out what c is?
If we had a variable.
The initial condition.
If you had an initial condition, you could. Do we have one?
No.
I don't think so.
Yes.
Did we?
Those 10 teddy bears. Grizzly bears. I always switch them to teddy bears. Teddy bears wouldn't die.
Teddy bears are cute.
I don't know about that. I want to do one more bit of calculus magic here.
Oh,
I'm going to multiply
just don't
by
go over there.
1 over c e to the negative 0.1 t.
Wait, what?
1 over c e to the negative 0.1 t. Legal?
Oh,
I didn't say is this the thing that you thought you would be doing, but is this legal? Why, Victoria?
Because in that way you're canceling, or in other words, you're moving the denominator to the numerator,
Okay.
and you do the 1 over c times e to the power of negative 0.1 t to cancel out.
Okay, my question is this legal?
Yeah.
This is fancy one. It is not anyone's choice for fancy one except for mine. But watch what happens. And I think, Victoria, this is what you were alluding to. 100 c e to the 0.1 t times 1 over c e to the negative 0.1 t. 100 c times this times 1 over c e to the negative of that.
Can't 1 over c and c cancel out?
C times 1 over c. I want to be careful with this canceling. C times 1 over c is really 1.
Oh,
Right? So I've got 100. C times 1 over c is 1. E to the 0.1 t times e to the negative 0.1 t.
1. No.
I'm multiplying and the bases are the same. The rule is add the exponents. So you get e to the 0. And e to the 0 is
1.
1. I wanted this 100 by itself for a reason. Because I want you to see something. Distribute the 1 over c e to the negative 0.12 through. 1 times all that is just 1 over c e to the negative 0.1 t. C e to the 0.1 t times 1 over c e to the negative 0.1 t is c times 1 over c, 1. E to the 0.1 t times e to the negative 0.1 t is e to the 0, which is 1. And for my last act of mathematical magic here, what do we know about c?
Is it constant?
I don't know anything about c. Nothing at all.
Can you just
So-
do supercharge?
We're going to call it super Charlie because it's a constant that you don't know divided into 1. So we're going to say that y is 100 over 1 plus c e to the negative 0.1 t. Almost done.
Solve for C.
If we have an initial condition, we can solve for c. Do we have an initial condition?
So t equals 0,
Wait.
y equals 10.
Okay, the initial condition says that if t is equal to 0, then y is equal to 10. So plug in the stuff that you know. 10 is equal to 100 divided by 1 plus, what is this, c times e to the 0? So e to the 0 is 1, so we just have c. My goal is to solve this for c.
So multiplying with 1 plus.
Yeah. You can either do your cross multiplying, or maybe the angels are whispering in your head. 10 equals 100 divided by something. What's down here? What has to be behind my hand? 10. So if that 1 plus c is equal to 10, then c has to be 9. So c is equal to 9. So your final equation is going to be y equals 100 divided by 1 plus 9 e to the negative 0.1 t.
Is that it?
Oh, you want more? Okay. I mean, we can go to like super logistic growth or something. Man, I just did all that without looking at my notes. And I think it turned out right.
3 times.
So let's see if it actually works. The things that we know, if this is logistic growth, I have an initial condition. The initial condition says if t is equal to 0, how many grizzly bears?
10.
Does that work? Let t equal 0.
Oh, is it?
E to the 0 is 1. 9 times 1 is 9. Plus 1 is 10. 100 divided by 10 is 10. Check. It satisfies that test, but there's another thing that we know. There's one more.
The max should be 100.
The max is 100. The limit as t approaches infinity of y is supposed to be 100. Does that happen? Imagine t approaching infinity.
Also, it's 0.
Negative 0.1 times infinity is like a negative infinity. If the exponent approaches negative infinity, e to the negative infinity approaches 0. 9 times 0 plus 1 is 1. 100 divided by 1, 100.
So the AB kids, we're gonna do this like next month.
Not with 7th period, no. This is not the way to start the 7th period.
Oh,
I would break them. They would walk out.
Leave this. Leave this.
Anyway, this is one problem.
I told them to copy it down. This is what they're going to be working on.
Here's the exciting stuff, though. My pattern matching people, I bet you're starting to see some things in this form over here. Or not.
The carrying capacity divided by.
This guy here is your carrying capacity. We'll talk more about this tomorrow. Tonight's homework has nothing to do with logistic growth.
Wait, class is over?
You will never do that again from start to finish. Tomorrow we're just going to generalize. We're going to go straight over to this part. Good times. Yeah. No.
Like, I just turned it off like.
Yeah, if you don't mind turning it off.